Now, back in chapter 6, we started talking about trusses, okay, which is essentially the first important application of the equilibrium conditions, okay, the equilibrium equations, right? Sum of forces equals 0, and sum of moment equals 0. Okay, so chapter 6 is really a real-world application of those equations, right? So you learn a couple methods, the joints method and the sections method, to analyze a bridge truss, right? And you'll be able to calculate the forces in a truss. Okay. Now, the rest of the chapter 6 is concerned with the framed machines, which is really concerned with multiple force members, right? But the analysis is exactly the same as the two force members, okay? And you know, like what we did for joint and the sections method, you know, for trusses. So there's really nothing much to it, you know. So it's exactly the same thing. So I'm not going to spend time doing that. Let's move on to chapter 7. Chapter 7 discusses internal forces. Now let's look at it more closely. Now, so far, what we discussed, okay, really from chapter 1 through chapter 6, are concerned with external forces on a rigid body. Okay, external forces applied on a rigid body. For example, a truss, right? So, you know, take a truss like this. You might have a concentrated load, right? Apply it in the middle, joint right here, and then at the two ends you have the reaction forces. That's it. These three forces are external forces, right? The applied load, concentrated load, and then these two reaction forces. So they belong to external forces. Okay, so this is a free body diagram for the entire truss. And we also have looked at internal forces at joints, right? So for example, the same truss, just that now if you look at joint, now each joint, right? Each joint is subject to internal forces. Now those forces come from this member, and this member, for example, for this joint, right? And then we draw a free body diagram for a joint, which is really the joint method, right? So we're going to draw, let's say, this joint, A, B, so this is joint B. So you have this force, and this force, and this force. So you have these three forces, okay? And let's say, you know, this is like this, maybe like this, right? So these three forces, okay, when you look at these three forces on the truss itself, which is really these three right here, they are internal forces, okay, internal to this entire truss. But if you isolate this joint B out here, okay, that's joint method, right? Now these three forces now become external force, okay, external to this joint, right? So really depending on what really is your free body diagram, right? Internal forces could become external forces, okay? So that's what we've discussed so far. Now, what happens inside a member? Okay, let's say I take this member right here. Okay, so C and D, member CD. So what we've discussed so far, okay, fine, you're able to figure out what are the forces acting here on this joint and at this joint. But what if I asked you, okay, so I take this CD member out, okay, put it here. What if I asked you, what is the internal force or internal forces somewhere inside the CD, let's say at this position? What are the internal forces? Can you tell me? What do they look like? Right? What are the directions and magnitude of forces inside? okay, of this member, CD. Well, that is really the main goal of this chapter, internal forces. Okay, we're trying to analyze what's going on inside a member. Okay, whether or not this member is subject to two forces, which is the two-force member. Okay, that's what we discussed, for a simple trusses, or multiple forces, like three-force member or more. Okay, so the whole point of this analyzing internal forces is that, well, as an engineer, you really need to look at what's going on, not just for a given structure, a given rigid body overall, but also what's going on inside, just so that you know exactly what kind of loading, what kind of forces exist at anywhere inside a member. Okay? And knowing that, you'll be able to design whatever that you're trying to design, okay, and more efficiently, okay, and correctly. Okay. Otherwise, okay, if you don't know how forces behave here or here or here, okay, and if you attach it to the wrong, wrong position, on the machine or so on, okay, things might fail. Okay. Another purpose of this studying internal forces is that by knowing exactly what kind of forces are acting inside a member, you will be able to figure out what kind of deformation, okay, will occur for this member in real life. Okay? How would this member CD tend to deform? Okay, will it tend to deform like this? Right? Or like this, right? Okay, that is, that's highly exaggerated deformation, right? But which way will it be, right? Or will it be like this, all right? Okay, so by knowing what kind of loading inside, okay, a rigid body, you will be able to figure out what kind of deformation will occur inside that member. Now, the study of this, the deformation, is actually in next course, mechanics of material. Okay, I believe it's CE 273. Okay, so let's get started. Now, the simplest case, okay, in analyzing an internal force is by considering a two-force member, okay, such as this. Okay. So, let's say I have a simple member, straight member, okay, call it AB. And this AB is subject to two forces only. And since it's subject to two forces, the only type of forces that can exist is either compression or tension. Okay, no other way about it. Okay, let's say AB is under tension. Okay, so for a free body diagram of AB, I would naturally just draw these two forces. That's it. Okay, so I'll call it F and F. Exactly identical in magnitude, okay, but opposite direction. Right, so it tends to stretch this member AB. That's why it's under tension. Okay, so now this free body diagram for the entire rigid body AB is complete. That's it. Okay. Now, what if I'm interested in looking at what's going on at, let's say, this position, okay, inside of this member AB, right here. What's going on? What kind of forces exist? What you do is you draw this dashed line as if you take a saw and cut it through this plane right here. Okay? Try to cut it open. And then what you get is two sections now. Okay, this section and this section, right? And let's call this point C. Okay, C for cut plane. Right? So now, from one rigid body, I get two rigid bodies, right? Two sections. And for each section, I can actually draw a free body diagram. So, free body diagram number 2, let's say, I'm going to draw this section first. So, AC section. Okay. So I can draw the forces for this AC section and try to see what's going on. Okay, right here at this point C. I can also draw a third free body diagram where I look at this top section, CB. C. Okay. All right. So let's look at this. Now this section AC has a force coming out of this A, right, from this free body diagram number 1. So that's my F. Now, you recognize that this section AC is a straight section, just like AB, okay? And a straight section having this force, F, coming out of this A. In order for this section AC to be in equilibrium, that is, my AC is not moving, right? AB is not moving, that's why AC cannot move as well. So, AC must also be a two-force member. Therefore, there has to be a force coming out of C this way, equal to opposite of this force. And that's also F. So if F is 100 pounds, this other F is also 100 pounds. Okay, acting the opposite way. That's it. So there you have it. This is the internal force at this position C, at this cut plane C, inside of this member. Okay. What happens here though? This CB section. Okay. Same deal. Let's say I know that there's just force F coming out of this B right here, right? CB is also a two-force member. Therefore, there has to be another force, equal but opposite, acting on this point C right here, so that this CB is in equilibrium. Okay? And that's it. This little guy right here, this F, is an internal force, okay, at C. Okay? So this force is an internal force. Now this force is also an internal force. Just that, in looking at this free body diagram for AC, this force has become an external force, external to AC section. However, this guy right here, this F on top, is an internal force internal to AB member. Okay? Similarly, this F right here is also internal to AB, but is external to CB. Okay? So now, when I combine these two together, this guy and this guy cancel out. This internal force and this other internal force will cancel out. Okay? When I look at this entire AB free body diagram. Okay? And since they cancel out, they don't exist in here, in this free body diagram for AB. Okay? So, that's the simplest analysis, okay, of internal forces inside a two-force member. Okay? And I can ask you to find what's going on here also, right? Or here, or here, or here. Any point, anywhere inside this member AB. Okay? And use exactly the same analysis. Okay? In fact, at any point